Somewhere past the orbit of Jupiter right now, there is an object moving away from our sun that scientists spent the back half of 2025 repeatedly describing in published, peer-reviewed papers as puzzling, not once, repeatedly across multiple independent studies from multiple research teams working with different telescopes on different continents. It arrived from outside our solar system entirely. It is carrying chemistry that may predate our own sun by billions of years. And one specific detail buried in its gas plume proved strange enough that a Harvard physicist publicly raised the possibility it might not be natural at all. Before going further, it's worth being upfront about something. Nothing about this object has ever posed any danger to Earth, and NASA and the European Space Agency have both said so plainly, repeatedly, throughout its entire passage through our solar system. What makes this story worth 40 billion kilometers of attention isn't threat. It's the fact that an object this old, this chemically strange, and this thoroughly studied has never crossed our path before, and may not again for a very long time, if ever. The story begins on July 1st, 2025, at a modest survey station in Rio Hurtado, Chile, run by a network called ATLAS, short for the Asteroid Terrestrial Impact Last Alert System, a set of telescopes whose entire job is scanning the sky every night for anything that might be heading toward Earth. That night, it caught a faint point of light moving in a way that matched nothing in its catalog. Within days, astronomers worldwide had confirmed what the object's orbit was telling them. It wasn't looping around the sun the way every native comet and asteroid does. It was moving on a hyperbolic path, a wide open arc, the kind of trajectory that only makes sense for something that arrived from outside the sun's gravity entirely and is simply passing through on its way somewhere else. It became the third confirmed interstellar object in recorded history, following a strange, cigar-shaped visitor called Oumuamua in 2017 and a more ordinary-looking comet called Borisov in 2019, and was named 3I Atlas, the I marking it as interstellar, and the 3 marking its place in that short sequence. Later analysis of older sky survey images found faint traces of the object stretching back 55 days before its official discovery date, meaning it had been sitting quietly in astronomical data the entire time, unnoticed, until someone finally knew what to search for. At the moment it was found, 3I or its Atlas was already moving at roughly 221,000 kilometers per hour, and it was still well outside Jupiter's orbit. That speed alone told researchers immediately that this wasn't a local object. Comets native to our solar system get flung around by planetary gravity, but they don't arrive already moving that fast from that far out. Something else, some event entirely outside our solar system, had accelerated this object long before it ever encountered our sun. By October 2025, astronomers had worked out its orbital eccentricity, a number describing how stretched an orbit is at roughly 6.1, making 3I's Atlas more extreme in its trajectory than either Oumuamua or Borisov before it, the least gravitationally bound, most aggressive path of the 3 confirmed interstellar visitors humanity has ever recorded. It's worth pausing on how different those 2 earlier visitors actually were, because it puts this third one in real context. Oumuamua, spotted in 2017, tumbled through its brightness cycle in a way suggesting an elongated, almost cigar-like shape, showed no visible coma or tail at all, and displayed a faint, measurable acceleration that couldn't be fully explained by gravity alone, a genuine mystery that generated its own wave of headlines at the time. Borisov, found in 2019, behaved much more like an ordinary solar system comet, complete with a conventional dusty tail and chemistry that mostly matched what astronomers already expected. 3I Atlas doesn't fit neatly into either template. It has an obvious, active coma like Borisov, but a chemical fingerprint and an estimated age that place it in an entirely different category altogether. The first real research milestone came about 7 weeks later when NASA turned the Hubble Space Telescope toward the incoming object in August of 2025. Hubble couldn't see the solid nucleus directly, since a fuzzy cloud of gas and dust called a coma surrounded it, the way it does with most active comets. But by carefully modeling that glow, astronomers placed rough boundaries on the icy body underneath, an enormous range running from roughly 440 meters to about 5.5 kilometers across. That wide uncertainty tells you something important on its own. This object was hard to pin down precisely because, unlike anything we've studied close to home, researchers had no prior data on it whatsoever, nothing to compare it against. Then came the chemistry, and this is where things started genuinely surprising the people studying it. As 3I Atlas moved closer to the sun and began warming, both the James Webb Space Telescope and NASA's newer SPHERE-X mission examined exactly what gases were pouring off it. In a typical solar system comet, water vapor dominates that outgassing, since water ice is the most common frozen material comets carry. That is not what these instruments found. The coma of 3I Atlas was overwhelmingly carbon dioxide, making up roughly 95% of the detected gas, with water accounting for only a small fraction. Webb also picked up tiny water ice particles and carbon monoxide gas mixed into the coma, suggesting a genuinely layered, complicated mix of frozen materials warming up together as the comet approached the sun. A carbon dioxide-dominated coma at that distance from the sun is unusual, suggesting the object formed somewhere extremely cold, far colder than the region where our own solar system's comets condensed, in a part of a stellar disk where carbon dioxide ice could form and survive more easily than water ice ever could. Researchers who authored the paper describing this detection, released as a preprint in late August 2025, described it as evidence that 3I Atlas came from a formation environment entirely unlike anything in our solar neighborhood. SphereX followed up the next month and confirmed organic molecules present within the coma as well, adding yet another layer to the chemical picture. The object's true age took nearly a full year of follow-up work to properly nail down. Early estimates, based purely on its orbit and the population of stars in the region of the galaxy it appeared to come from, suggested an age around 7 billion years, already older than our own solar system. The real confirmation came later, once Webb's near-infrared spectrograph observed the comet in early August of 2025. Its mid-infrared instrument revisited it in mid-December after the comet had swung past the sun and was heating up from fresh solar exposure. Researchers led by Martin Cordiner at NASA's Goddard Space Flight Center used that data to measure the ratio between two forms of carbon in the escaping gas, ordinary carbon-12 and the heavier isotope carbon-13. Almost all the carbon in our galaxy originates inside stars more massive than our own sun, and the balance between these two isotopes shifts gradually over cosmic time as successive generations of stars live, die, and enrich the galaxy with new material. What Cordiner's team found was a carbon isotope ratio containing far less carbon-13 than anything measured in our own solar system, or even in the young planet-forming disks currently observed around other nearby stars. Working backward through models of how the galaxy's chemistry has evolved, they concluded the object likely accreted its ice somewhere between 10 and 12 billion years ago during an early, intensely active period of star formation astronomers call cosmic noon. For context, our own solar system is about 4.6 billion years old, and the universe itself is roughly 13.8 billion years old. This comet may have already been drifting through interstellar space for longer than the sun has existed at all. The team published these results in the journal Nature in June of 2026, and Cordiner told reporters at the time that it might be, in his own words, the oldest object ever observed passing through our solar system. Alongside that carbon result, Webb's instruments picked up something else in the water. 3I Atlas was releasing. The ratio of deuterium, a heavier form of hydrogen, to ordinary hydrogen came back significantly higher than what's typically found in solar system comets, with some analyses putting the enrichment at roughly an order of magnitude, greater and other estimates going even higher still. That kind of deuterium enrichment tends to form only in extremely cold environments, colder than about negative 243 degrees Celsius. Combined with the carbon isotope data, it painted a consistent picture, an object that formed somewhere unusually frigid and unusually long ago, in a part of the galaxy current models associate with the galactic thick disk, an older, more scattered population of stars than the flatter disk our own sun belongs to. Daryl Seligman, an astronomer at Michigan State University who was not involved in the nature study but has studied the comet extensively, told reporters that before these measurements, getting this kind of detailed information from an interstellar object was something scientists could previously only dream about. That's already a great deal to absorb, but the detail that actually pulled 3I Atlas out of specialist journals and into mainstream headlines came in October of 2025, when a research team using the UVES spectrograph on the European Very Large Telescope in Chile detected something in the comet's coma nobody expected, a plume of nickel gas, later corroborated by additional data from the Keck-2 telescope in Hawaii. On its own, nickel vapor isn't shocking. It has been seen before in a handful of solar system comets, including Borisov. What made this different was what was missing. Every previous time nickel vapor has been detected venting from a comet, it is compared with iron vapor since the two metals are forged together inside dying, exploding stars and travel through space bound to each other as what researchers sometimes informally call cosmic twins. N3I are Atlas. The nickel signal was strong and the iron signal was nearly absent entirely. Astronomers scrambled to figure out how that was even possible. Since comets are generally far too cold for solid metal grains to sublimate directly into gas, something had to be releasing that nickel through a different chemical pathway, most likely a nickel-bearing molecule that breaks apart more easily under sunlight than whatever compound was holding the iron in place. There is a known, if unusual, natural process involving compounds called nickel carbonyls that could, in principle, explain low-temperature nickel release without any accompanying iron, and most astronomers studying 3I Atlas consider it the most likely explanation, alongside other refractory nickel-bearing minerals that may simply behave differently than iron-bearing ones when heated at extreme distances from the sun. But it's worth being honest that at the time of these observations, researchers had not fully confirmed which specific compound was actually responsible, and several published papers described the detection using words like extremely puzzling, because nothing previously catalogued in our own solar system quite resembles it. To understand why this matters chemically, it helps to know how nickel and iron normally behave in a comet. Both metals typically start out locked inside solid, refractory dust grains that require intense heat to vaporize directly. At the distances where 3I Atlas still sat tens of millions of kilometers from the sun, that kind of direct vaporization shouldn't have been happening to either metal at all. The leading natural hypothesis holds that the nickel wasn't escaping as bare metal, but as part of a more fragile, low-temperature molecule capable of breaking apart and releasing nickel atoms under far weaker sunlight than would ever be required to free iron from its own considerably more stable compounds. If that mechanism holds up under further study, it would represent a previously undocumented category of natural comet chemistry rather than evidence of anything manufactured. Researchers have also noted fainter traces of this same nickel-dominant pattern in Borisov as well, suggesting this could be a broader feature of comets forming outside our solar system generally, rather than something unique to this one object. Harvard theoretical physicist Avi Loeb, who has spent much of his career searching for potential signs of extraterrestrial technology, and previously raised similar questions about Oumuamua back in 2017, pointed out publicly that nickel without iron is otherwise mainly associated on Earth with industrial refining processes, and he raised, repeatedly and openly, the possibility that this could indicate something artificial. He also pointed to the comet's trajectory, which passes unusually close to the plane in which the planets orbit, as another data point he considered worth flagging for further scrutiny. It's important to say clearly that this remains a minority position within the scientific community. The overwhelming majority of astronomers actually working on 3I Atlas, including the very teams who made these detections in the first place, favor natural chemical explanations rooted in the comet's unusual, ancient, and extremely cold formation environment, not a manufactured origin. And several researchers have separately pointed out that survey systems like Atlas are simply more likely to find objects whose paths happen to cross close to the ecliptic, because that's the region of sky searched most intensely to begin with, which weakens the trajectory argument considerably. Still, the underlying anomaly itself, nickel with essentially no iron, remains real, measured, and not yet fully explained, down to the exact responsible molecule, which is precisely why this particular detail kept generating headlines through the back half of 2025. The seriousness with which working scientists treated this open question deserves its own mention. A team of researchers actually pointed the Allen Telescope Array, a radio observatory built specifically to search for potential signals from extraterrestrial technology, directly at 3I Atlas during its passage through the solar system, systematically scanning across a wide range of radio frequencies for anything resembling an artificial transmission, dedicating real, competitively allocated observing time to the effort rather than treating the question as unworthy of formal investigation. This wasn't a fringe stunt. It was a peer-reviewed technosignature search, conducted using the same rigorous methodology applied to any other candidate target the array has ever studied, following established protocols for ruling out interference and confirming any genuine signal before publication. The result was a clean non-detection. No artificial radio signal turned up coming from the object, at any frequency the array was capable of monitoring. That detail rarely makes it into the dramatic headlines, but it matters because it shows that when a legitimate scientific question got raised, however unlikely the eventual answer, the response wasn't idle speculation. It was pointing a real instrument at the object and reporting exactly what was and wasn't found, then publishing that null result openly for anyone to review. The comet's physical size and mass only came into sharper focus after it had already passed its closest approach to the sun. Early observations noted that 3I Atlas wasn't developing the kind of long, dramatic tail that sunlight pressure typically pushes off an active comet, which briefly fueled speculation about whether its nucleus might be unusually massive or its surface unusually resistant to that pressure. Once the comet moved past perihelion and astronomers could finally separate the glow of the solid nucleus from the surrounding coma, using Hubble images gathered across multiple visits in late 2025 and early 2026, they arrived at a considerably more refined figure, an effective diameter of approximately 2.6 kilometers. Narrowing that earlier wide range significantly and confirming this was a genuinely large object by interstellar standards, notably bigger than Borisov, even if the more extreme early mass speculation wasn't what the refined measurements ultimately supported. This particular comet also received a level of direct close-up scrutiny neither of the two interstellar objects before it ever got, thanks largely to the sheer number of spacecraft already operating throughout the inner solar system by 2025. On October 3rd, 2025, during its closest approach to Mars, 3I Atlas passed within about 29 million kilometers of the planet, close enough that NASA's Perseverance rover, along with multiple Mars orbiters, managed to capture images of it, marking the closest any operating spacecraft had ever gotten to a confirmed interstellar object. The European Space Agency's JWST spacecraft, already en route toward Jupiter's icy moons, also attempted its own observations as the comet passed nearby, using its cameras, spectrometers, and particle sensors to add yet another vantage point to the growing dataset. Ground-based observatories joined in as well, including the Gemini North Telescope in Hawaii, which captured a detailed image of the comet in late November 2025, carefully processed to correct for the streaking star trails caused by tracking such a fast-moving target. So why should any of this matter beyond making for a compelling headline? Every comet native to our solar system formed from the same disk of material that built our planets, meaning studying them mainly tells us about our own local chemistry. 3I Atlas is different. It is a physical sample of material that condensed around a completely different star, under different temperatures, at a different point in the galaxy's entire history, and it drifted here across billions of years without ever being disturbed by any star's heat until now. That gives researchers something they've genuinely never had before, a direct chemical comparison point to test whether the process of building icy bodies works the same way everywhere in the galaxy, or whether it varies significantly depending on where and when a given star system happened to form. The nickel and iron anomaly specifically is forcing working scientists to reconsider assumptions about how metals get locked into or released from ice at extreme distances from any star A, assumptions that had been built almost entirely on a sample size of solar system comets alone. NASA and the European Space Agency have both been explicit and consistent throughout this entire story on one specific point. 3I Atlas posed no threat of impact at any stage of its passage through our solar system, and it never came remotely close enough to Earth for that to be a realistic concern at any point. Its closest approach to our planet coming on December 19, 2025, at a distance of roughly 270 million kilometers, nearly 2 full astronomical units away, more than 700 times farther than the distance separating Earth from our own moon. What's actually left behind, now that the comet has swung past Jupiter and continues receding into the outer dark, isn't a mystery solved or a threat avoided. It's a complete data set sitting in the archives of Hubble, Webb, and a dozen ground-based observatories, records of a piece of another part of the galaxy that happened to drift close enough for humanity to measure it once carefully and thoroughly before it disappeared for good, carrying 12 billion years of frozen history back out into the darkness it originally came from, never to pass this way again, its story now permanently recorded in journals and archives long after the object itself has faded beyond the reach of any instrument currently pointed at the sky.